Okay, here we go. Okay, I think we can get started.
Yes, you can start.
Okay, thank you. Yeah. Hello, everyone. Thanks for joining this session. My name is Cong Wang, and I'm a Linux kernel developer and a Linux kernel maintainer. So, today I'm going to talk about eBPF socket maps. In this talk, actually, I would like to present a very friendly introduction to eBPF socket maps. Let's get started. So for the agenda today, first actually I would like to give you a very high level overview of the eBPF socket maps, and then I will move on to a few different socket map programs, and I will after that I will talk about the eBPF Sockops, which is highly related to the socket maps, and after that I will provide about six examples to show how we use socket maps and the socket map programs and also the socket ops together to combine with different cases. And finally, I will provide a very short, brief history and also future directions for the eBPF socket map development. So if you are interested, actually, you are very welcome to join the discussion. Okay, let's get started. eBPF socket map. Before we start, so actually I make an assumption here, which is I assume you already familiar with at least know something about eBPF, and of course I also assume you already know a little bit at least about eBPF maps. Yeah, because eBPF socket map is only just a special eBPF map just to store the active sockets, and within the eBPF socket maps, actually it contains a set of the socket file descriptors, and these descriptors are explicitly edited by the user, whether it's directly with the file descriptor in the user space or with socket ops in the kernel space, either way. And like other socket maps, actually, we could use two. There are two ways actually to look up the socket. eBPF programs related to socket maps. So these programs are attached on top to the socket maps, and these four different programs are not very easy to understand. So this is why I want to highlight their difference here. The first one actually is what we usually call it. It's the message verdict. The message verdict actually is a verdict on the generic TCP socket message. So it operates on the message, but still on the TCP socket. So it's kind of generic because actually it could also be used for the kernel TLS as well. And the second type of program is the stream parser. So this is very useful. This is the TCP application protocol parser. So with this program, actually we could actually parse the application protocol, like HTTP, FTP, this kind of protocol within the kernel. So this is very powerful. And the third one is a stream verdict. Like the suggested by the name. Actually, it's also operates on the TCP socket, pretty much like the stream parser. However, it's a verdict. Just to decide, hey, whether we should, what kind of policy should we apply to this packet. And the last one actually, which is the new one, is a very generic verdict on the socket buffer, and it could apply more than just the TCP socket. So this is why it is called SKB verdict. So we will go provide more details later when we go over each of them. And the Sockops actually is pretty much just a set of the socket layer hooks, but only for TCP socket. This is pretty much all the information we have related to the socket maps, but there are still a lot of details we will go over later. And before we move on to the eBPF socket map programs, one thing I would like to mention is actually eBPF socket map programs. They are very special, so they are not like the other eBPF program, because for the regular eBPF programs, actually we pretty much just attach the eBPF program to different quite some different places of the different hooks within the Linux kernel. However, for the eBPF socket map programs, they are not attached to literally not to any kernel hooks. They pretty much attached to the socket maps. So these four programs are actually are the test type. They are not actually the program type. They are just the we load the program but attached to different types. Although and of course could be the same type of the socket map, and they operate on the packet flowing within the socket stored in the socket map, and they actually could enable the socket to socket redirection, and they could actually provide kind of a fine-grained control over the socket if we use for example the hash table to look up the socket map. And one last thing before we move forward actually I have two messages is because there is another literally another socket map which I'm not going to cover any more details, but I just want to mention it here for completeness, which is the XTP socket map. So this is yet another very special socket map, but this is even more special because it's only for the XDP socket. So, and it's actually used for the XDP packet redirection for the to the XDP socket, and there is also a eBPF helper to use together with this socket map as well, and it's very different from the socket map I'm going to talk about in details today. So today this one is not within the scope of discussion because it's too special. Okay, let's move on. So the first eBPF socket map program I'm going to talk about is the message verdict. So this one actually is also very interesting. So the reason why this one is interesting because it actually is one of the probably the only one apply on the TX direction. So this one is applied when we transmit the here actually is the message because this one actually applied very early on the transmission path, even before the SKB, the socket buffer is allocated. So that's why actually this socket map program applies on the socket message, not on the socket buffer. So this is very special because it's too early on the transmission path, and there is not even a socket buffer allocated yet, and it operates on the TCP socket, and also it applies quite a few policies on the message as well. So we can actually decide where this message to go, or we can simply drop this message. So this program could support two kind of scenario. One is regular TCP, the other is the TLS within the Linux kernel. However, is still on top of the TCP. So the most common use case for this one is actually because it's too very early and it's very high level on the TCP socket layer. So actually, we could actually do kind of socket layer redirection because if we use other eBPF socket map programs, they apply to different places. Although they are not attached to the hooks, but they apply to different locations. And the other use case is actually we could actually filter the content because this one applies to the socket layer. So that means we have all the socket layer information, like the HTTP related stuff. If we want to use this for HTTP socket, and of course we could also use kind of for the read limiting as well, but for the socket layer. This is also very useful because this is pretty much the only one we have on the transmission side. And the next one here is the SKB verdict. So this one is also very useful because this one, like I already briefly mentioned, this one is very generic. So this one does not only apply to the TCP socket, but also literally to all the type of the socket. However, it still requires each of the socket to explicitly support this kind of socket member operation. So that's why we so far we kind of only have four different socket families to support this. So this one is very easy to use, and because for the first reason, because it applies to the socket buffer. So I assume you are already familiar with socket buffer. So it's definitely easier than the socket message, and it's applied on the receive path. So that's why when you consider the policy to apply to different places, you need to think about what is the location, what is the direction, and like I mentioned, this is very generic. This is also a very good thing because if you want to put a different socket within the map, you don't need to worry about the map anymore. Just worry about the type anymore. Just use this one. And so far, there are only four socket families support this one: the TCP socket, the UDP socket, the Unix domain socket, and the VSOC. So. And this one actually could, with this socket map program, actually it could operate on the entire socket buffer. So we could have the use the whole package content, for example, for filtering, parsing, and the most of the common use case for this one is actually, we use this one for the heterogeneous socket redirection and splicing because this is the only one we could actually put different sockets within a map and do some redirection and splicing with them. The other map or eBPF programs, the other socket map programs don't allow this kind of operation. And this one actually is also for the could also be used for the socket layer filtering and literally the load balancing as well, but this one is for the receive path. And the third one we are talking about here is the SKB stream vertical. So it's pretty much similar to the previous one, except actually this is only for the TCP socket. And the reason why this one only applies to TCP socket is because of the history. So in the past, this one actually was invented before the previous one. So that's why this one actually was only restricted, was only limited for the TCP. So actually, I introduced the previous one, the generic one, which could actually apply to different type of the socket. So their usage is pretty much the same. So there, other than the the socket type support here, there's literally no other difference. So and also another thing actually I need to mention is this one is also special because it could be combined with the next one we are going to talk about. So because when we use the SKB stream parser, actually it's kind of mandatory. We need to combine it together with this one. However, this one I don't think is probably is not necessary to combine with the parser. So for the use case here actually is pretty much similar to the previous one, except this one is only for the TCP. So this one also we could actually do some protocol. I mean the layer 4, layer 7 protocol aware of message filtering and also do some routing based on the layer 7 headers as well. So the last one is the SKP stream parser. This is also the very interesting one. So this one, like I already briefly mentioned in the beginning. So this one is the only one we have within the kernel that could parse the layer 7 headers within the kernel. So that's why I call this one a true parser. So the main purpose of this program is pretty much actually is exactly designed to teach the kernel to learn where is the message boundary, where is the layer 7 message boundary. Because, for example, for the HTTP headers, the Linux kernel definitely does not have no idea about how long about I mean the content of the HTTP header. So with this one, actually, we could actually parse the layer 7 header like the HTTP header and tell the kernel, hey, how long is this message supposed to be? Because with this information, the kernel could actually assemble the SKB together. Because actually, the one significant difference between the application layer and or the layer 7 or between layer 7 and layer 4 is actually in the layers 4, we don't care about the boundary. So they are just a stream package. There is no message boundary in the layer 4. However, in layer 7, the boundary actually is defined by the protocol. For example, HTTP definitely has some, HTTP header length, this kind of stuff. So this is important because if this differences could actually make a significant difference when we pass the layer 7 message within the kernel, because the packets first need to be assembled for a whole message for the program to pass. Otherwise, we could actually parse a partial layer 7 message within the kernel, which is usually not what we expect. So this is why we have to use this parser to tell the kernel, hey, this is the boundary of the message, and you need to assemble the SKBs together to respect this layer 7 boundary. And this one actually also operates on the SKB buffer, and this one actually, like I mentioned, this one must be paired with the verdit. So this one is just the parser tell the boundary, tell the kernel where is the boundary. Actually, usually when it is combined with the verdit, actually it is the verdit program usually do something, after it has a complete layer 7 message. So this is how it is usually used. And the use case actually is become very, very interesting with this one because with this one, actually, we could parse the application protocol within the kernel. For example, you might find it very interesting to parse the Redis message within the kernel because literally you can do the Redis caching, this kind of Redis stuff within the kernel. And the other use case is actually we could extract the application protocol metadata within the kernel as well, whether it's for filtering, whether it's for the load balancing. So I will actually show an example later. So move on to the socket ops. So the socket ops actually is, like I mentioned, pretty much a set of the operation on the socket layer, but only for the TCP socket. So it hooks to different events of the TCP socket lifestyle. So and the reason why I need to introduce it here because it usually actually it is common to combine the socket ops together with the socket map to get some more powerful use case. So that's why we need to mention it here. And so when they are combined, actually we do could produce even more wider use case. For example, actually we could apply the socket, different socket options to each different socket so that we could actually tune the socket, the TCP socket with better granularity within the kernel. And like I mentioned, it usually typically is combined with the socket map together. So there is they collaborate together with one particular concept called the BPF socket ops. So this one actually is supplied by the socket ops. However, it is also accepted by the socket map helpers. So when we insert the socket from the socket ops to the socket map, actually we could use this data structure. And because of that data structure, that means we would no longer need a file descriptor anymore, and that also means it is completely transparent to the application. So that's why actually if we want some transparency for the application, actually we should consider this one instead of using the regular socket maps, which definitely directly operates on the file descriptor. And because this one actually, this set of hooks actually is attached to the each C group. So the granularity here is per C group. So this is also an advantage if you have container stuff. Okay, so let's look at the different hooks here. So actually here I listed pretty much three sets of the socket ops. So each of them actually serve different purpose, and each of them contains quite a few hooks. And the first one is the connection setup. So this is very important because actually, if you want to hijack the TCP connection, this is probably you want to consider this set of hooks. So when the TCP connection setup, there's three-way handshakes. During different stages, actually, the Linux kernel could could allow us to use this kind of three different hooks to attach the eBPF the socket ops program, different socket ops program to different event. So the first one is when we establish an active connection, and it will be triggered. This hook will be triggered. So if we load some programs there, actually we could do something after an active TCP connection is established. For example, maybe we if this is a client, you probably want to, for example, insert the client socket to the socket map to do something. So something like that. And the second one is pretty much similar to the first one, except it's for the passive connection, which is, for the server. So when the server establish some accept some connection, so this hook is triggered. So this is also very useful because, for example, if we want to do something like, let's say, on the Redis server, so this one actually could be very useful. Each time when the server spawn a new socket, actually we pretty much want to insert that socket into the socket map. For example, the Redis, if we want to pass the Redis protocol. That means definitely we want to put all the Redis server socket within the socket map to do this kind of parsing, caching as well. And the last one actually is related to connect. Actually, so when we use the client to connect the TCP socket, and this one actually triggered before the connection is fully established. So that's why this one is attached to the connect system call before it completes. The next set of the hooks actually is related to the TCP state, because TCP socket is the very stateful socket. So when we switch the TCP state from one to the other, actually there is a literally very generic one for the eBPF hook, so that we don't have to write quite different hooks for different states. So this one actually provide a literally generic one, so that you can decide, hey, whether this is, whether the desired state transition is what you want. So this is literally the generic one. So this one is also very helpful if you want to, monitor all the TCP socket state change, and for whether it's for the connection tracking, for more performance monitoring, this kind of stuff. And the other one here is related, pretty much similar to the connect one, but this one is related to lesson. So this one is pretty much hooked on the lesson system call, and which is typically on the server side as well. And the last set of hooks I'm going to introduce here is, the related to the TCP, pretty much congestion control. So, TCP definitely offers the congestion control as well, congestion control related hook as well. So that means when the TCP triggers, for example, some retransmission, or this time it measures the round trip time, it will also trigger different kind of hooks as well. The first one is triggered when, every time when we measure the round trip time. So this is very useful if you decide, to measure, measure and store the round trip time by yourself. And of course, when it combines with the socket map, you could actually do something, for the whole set of the socket related to the congestion control as well. And the second hook here is related to the retransmission timeout. So this is also very useful for the TCP congestion control. So if you want, for example, to modify the RTO related parameter, and or if you want to customize your own congestion control, this is also very useful. And the last one is called pretty much for the packet retransmission. So this is also useful, at least for the if you want to count some retransmission statics, or if you want to customize something based on the packet retransmission, this is also very useful as well. Okay, so the last set of the hooks is related to the TCP option. So this one is also very useful when you want to customize some your own TCP auction, because traditionally if we want to implement some our own TCP option, actually that literally you need at least to write some kernel module. Actually, with this set of the Sockops programs, actually we are able to write our own. It's not actually which. It's not just for the TCP option writing, but also for parsing as well. So it's paired. So when we have our customized TCP header options, actually it's not that we should only insert the options there, but on the receiver side, we also need to parse and interpret it correctly as well. So that's why this set of the hooks actually provide this kind of operation. So they are very, very useful if you have own information within the TCP option to carry over the network. So this is a little bit complicated because it also related to the length of the header as well. But I think as long as you read into the document and with some examples, actually they are not that complicated. Okay, I think it's time when we go over all the go over quite some of the use cases, because we after this amount of information, I think people, if you this is if the eBPF socket map is new to you, I think you are probably still don't have that much specific idea about how exactly we should write eBPF maps and how exactly we should use the eBPF socket map program together with the socket map. So now they are the examples I'm going to talk about. So the first use case or the first example I'm going to show here is the socket splicing. So this is also a very popular use case because socket splicing is very useful, and compare with the Eurospace socket splicing, within the kernel, this is definitely more efficient because within the kernel there is no context switch, so we don't have to switch between Eurospace and kernel space and going back. So within the kernel, everything flows within the kernel space. So this is actually very useful even in the real world as well. So the socket splicing I'm going to talk about here is pretty much we just want to forward the data within the different socket with are stored within same socket map. Here, to simplify the example, I just provided two sockets. I know it's probably is not real. However, just want to simplify, just give you some very brief idea, like how we should splice two sockets together. So here, actually, because like I mentioned, I prefer use the generic one, which actually is the SKB verdit. So and we don't actually need to care that much about the type of the socket within the map. They are pretty much as long as the socket is family itself supports the socket op operation, we are good here. And the because I highly simplify the example here, so that's why actually I don't actually use the socket ops, because that will actually need to combine more piece of the eBPF program. So here I just want to simplify this example. So that's why I still assume actually we should actually use a traditional file descriptor, and that means it is the Eurospace responsibility to insert the socket file descriptor within the map, which is actually not showed within the example. So this is the code. So the code here actually is pretty simple because I highly simplify here. And the first thing you probably notice is on pretty much on the top the type of the map is the socket map. So here actually we use the traditional socket map, which is based on the index, not a hash table. So, and here, like I mentioned, I only provided two socket within the socket map. So the max entry is the max number of the entries is only two, and the key actually is pretty much the index. The value is pretty much the file descriptor. So here actually below is the eBPF socket program, which actually should be attached to this socket map. And this program, like I mentioned, it should be SKB worded. So that's why in the section actually is called SKB. So this string should be mapped to the SKB worded. And within the function, like I mentioned, this program operate on the socket buffer. So that's why we have a socket pointer to the socket buffer in the context. And here actually I just use a very naive way to do the redirection. Just simply redirect to index one. So here actually I use the helper BPF redirect map to redirect to the to the socket which is index one here, and if the redirection success we pass, and otherwise we drop the packet. So this is a very simple one, and very efficient socket splicing example. Okay, so the next use case or the next example I'm going to show here is a slightly complex, and which is load balancing. So actually here in this example, actually I will show we try to do kind of load balancing between different sockets within socket map. So actually we want to distribute the connection to different back-end socket, and this back-end socket actually they are stored in a socket map, to group together, and we select the back-end based on a very simple round robin algorithm, highly simplified. And of course we also redirect the message with the another eBPF helper here. So here is the example. So this one becomes slightly more complex because like I mentioned, this one is uh, for the load balancing, we actually need two maps. The first one is through the socket map. We need to store the socket. So all the backend socket are should be stored within the socket map. The other one is another regular eBPF map. Which is an array here. Which we need to record the index. In some round robin way, so that we could do the load balancing. So the eBPF program I pick here actually is the message worded. So that means this one applied to the transmission on the transmission path. So as you can see from the section here, this one actually is for the message worded. So, and for the message worded, actually it applies to the SK message. It's no longer the SKP buffer anymore. So that's why the parameter or the context is very different now. And so for the program itself, actually, like I mentioned, because it's load balancing, so the first thing is we need to look up the array to say, hey, where is the last index? So we need to do the first thing we need to do is we need to look up the array and find out the index. So once we find out the index, we need to move to the next one. And after we move to the next one, we also need to update this array accordingly as well. And finally, after we retrieve the the last index of the socket from the array, we need to do the the redirection. That's how we achieve the load balancing. Distribute the packets. Kind of in a round robin way. So in this example, actually, because we use the message verdict. So that's why, there is another eBPF help here to do the redirection. It moves the message, redirects the message to the specified index here. So I hope this example is more useful to you to show how we should use the eBPF socket maps. Okay, so the next one actually is also pretty much a very common one. So this one is the packet filtering is also very common for the eBPF programs within the networking subsystem. So however, because we are talking about the socket map here, so pretty much this one here this one I would like to show you is how to do the packet filtering for the receive path on the socket layer. So that's why I will use the SKB verdict here as an example. So and in this example also I specifically designed a very artificial use case. So in this case, actually, I would like to pass the TCP header to find the destination port, and if the destination port is some port we disallow, we just drop the packet. I know this is very artificial, and also it's not very far from the real use case actually. So the program itself is also very easy because the filtering generally is easy. So here actually the most complicated part is the header parsing. Yeah. So let's take a look at the program here. So the program, the type, like I mentioned, is the SKB verdict. So and it applies to the to the SK buff, so it's not the SK message. So after we have this context, actually we need to rely on the some SKB helper to do the packet parsing. So here we use the SKB the eBPF helper BPF SKB load bytes to load some specific data from some offsets, and I know this case is highly simplified because the TCP case actually it could be more complicated than this. So we just parse the TCP destination port and retrieve the destination port to our local variable, from the package. So after we retrieve this destination port, we just simply check whether this is, 8080. So I know this is very naive. So, however, just to show you how we should, do the parsing and, packet filtering. And if this is, that is the case, we just drop the package. So this is also very, very simple. Another common use case is for the socket map is the socket monitoring, because actually these kind of programs are all for the socket layer. So actually, to monitor the socket actually we could consider using the socket map programs, or otherwise you could also use some trace point for the socket layer as well. That could also work. So and this one actually could collect the real-time socket metrics, like the bytes of transmitted bytes, and we update the socket. We store the stats within the socket map, and we just use the look up the stat map stat map using a socket ID, and we just increase the counter, every time when we transmit some message here in this example. So this is example is also very simple. So one big difference with the previous example is actually here I started using the hash table, no longer the the index or the array anymore. So that's why the map here is a hash map. So here actually we the EBPF the program type we use here is ASCII message. So we want to monitor the socket layer one, and it's for the transmission path, and it operates on the ASCII key message. So we use the pointer to the socket as a key. So we simply retrieve the key from the ASCII message. So we use this key to do the lookup on the stat map. So and the value of the map is the actual stats we want to store, and because the key is the pointer to the socket, so that means we do have a per socket stats in this case. So here actually I just want to count how many bytes we transmitted for each of the socket. So that's why we just simply increase the counter based on the number of the bytes within the message. So this is also very easy. Another example here, actually, I think this is very close to the real use case is layer 7 protocol parsing. So this one actually, I believe, is one of the most powerful use case provided by the socket maps. So in this example, actually, I would like to show how we should parse the thrift message. Thrift message actually is pretty much defined by almost entirely defined by the application. The Swift protocol provides a general framework, pretty much like the protocol buffer general framework for each of the application to define their own. However, in this case, actually, we highly simplify the case. It's not that we want to go that deep. So in this case, we pretty much only use some very simple type of the thrift message, and I just use some naive way to do some filtering based on the thrift protocol version. So this is also kind of artificial. However, I do believe this use case itself actually could show you some real world use case, to show how we should do filtering and parsing for layer 7 protocol. So let's take a look at this example. So this example actually contains two programs because, like I mentioned previously, the SKB stream parser must be paired with the SKB stream vertex to do the filtering and to do the parsing and filtering. So the first part I show here is the parser. So the parser here actually, here actually we need to, as you can see, the section part we need to explicitly tell the kernel, hey, this is the SKB stream parser we want to use, and it also operates on the socket buffer itself. And here actually, because the thrift protocol has its own way to store the length of its frame, so that's why actually we need to load the thrift protocol frame size from the payload, which is actually the header of the which is the thrift header. So fortunately, in this specific case, the offset of the frame size is exactly at 0. So we just need to load load from offset 0 and load 4 bytes, which should be the size of the frame. And once we have the size of frame, actually we could tell the kernel, hey, this is how long the thrift a complete thrift message is supposed to be, because actually the kernel does not care about the boundary, to be honest. So in the real world, actually, I did say, one small Redis package got split into two parts, so that's very annoying. So that's why you probably definitely almost always want to use this one if you want to do the layer 7 parsing. So we need to tell the kernel, hey, this is how long it is. The kernel will behind the scene, the kernel will assemble, let's say if this one is not a complete one, it will assemble together with the next one, or or even after together to form a complete layer 7 message. So after we have a complete layer 7 message, actually we could be able to do some kind of policing, because we have a complete one, right? So in this case, like I mentioned, I want to do some more sophisticated parsing, to find the thrift header version, and check the version, and drop the packet is not expected version. This kind of slightly more complex, but definitely requires a very complete layer 7 package. So here actually we needed to tell the kernel this type is the stream verdict, and this one should be loaded together with the previous one to combine. And this one also operates on the SK buff. So this one actually pretty much the pattern is pretty much similar. We just need to load some part of the header, some application protocol defined, header at some offset, with some, in this case is also 4 bytes. And after we retrieve the version information, we just do some checking, and if this is not our expectation, just drop. So I know the use case is not is kind of artificial. However, it's still, I believe, is getting closer to a real world. Okay, another example I have here is the TCP hijacking. So this one actually, as you can see from starting from this one, actually, this one will be combined with the socket operation. Yeah, because we need to hijack the TCP connection. That means we need to have some way to learn, hey, when is the TCP connection established? So that's why starting from this one, I will show how we should combine the socket map together with the socket ops to, get some more useful examples. So in this one, actually, I would like to use Sockops to detect the new connection, and I will also store all the sockets in the socket maps, and I will also redirect the traffic through a proxy socket. It's also kind of artificial, but I think maybe there are some real use cases as well. So this is the code we have here. So this one is also slightly more complicated now, because like I mentioned, we need to combine the socket ops with the socket map. So that's why we see two different programs here in one page, and also of course with the socket map together. So the socket map here I use is still the very traditional, the array based one, and actually I only store one socket within this socket map. So the socket ops here actually here actually we need to tell the kernel this is the socket ops program, and this one actually this is how it get slightly more complicated now, because actually this one it accepts pointer to the socket option struct. So this one actually within this context, this one actually supplies a lot of useful information, like the operation. Operation is exactly what I mentioned before. In this one, actually, I want to attach it to the actively established connection. That means I need to explicitly check the operation within the code. So it's not like the other hooks which actually attach to different place. We just need to specify the attach type. This one is very different. So this one we need to explicitly do the check. So if this is not our expected operation, we just don't do anything, just return. So otherwise, we do something, right? We continue to do something. The first thing we need to do is definitely we need to retrieve the socket, right? So which is also within the context here. So after we retrieve the socket, we do update the map, and also here, we also need to store some flags here as well. And the next thing is, because this map, the proxy map is shared, as you notice, it is shared between this socket ops and also the other socket map program. So this is how they collaborate together. So in the socket ops, we update the socket in the socket map, and within the socket map program, actually we do some redirection on top of this socket map. So this is, as you can see, this is exactly what I want to show you with this example, how we should actually use socket ops together with the socket map. So in the socket map program at the bottom, so actually I attach it to the message verdict. So the attached tab is the message verdict. So it operates on the SK message. So and we do the SK message redirection within the socket map, because this socket map only contains one socket. So that means actually all the sockets for the we attach here actually should be redirected to the proxy socket within this map. Okay, so I think that's all the examples I provided today. So I hope these examples could give you some more specific information on how exactly we should use socket map, and also optionally combined with the socket ops. Actually, some of the example actually are pretty close to the real world. So I hope they are useful to you. And so the next thing I'm going to discuss is although socket map is very powerful, and it becomes more powerful if we combine with socket ops. However, there are still some limitations as well. Because when we use the socket map, actually we do realize there are some kind of pain points, some limitations I would like to mention, and I would like to give you some reminder to aware of this kind of limitation before you start using it. So the first one is there is definitely as I mentioned for a few times, there is definitely a very big difference between the socket meshes and the socket buffer. There are two different structures, so they are have very different layout, very different purpose. So the SK message actually was invented for the message verdict. So like I mentioned, in that context, there is no SK buffer involved. So that's why there is no SK buff in that context. So the SK message is still heavily used in the Linux kernel, even in the receive data path. So this is also a very sad fact because actually this is, in my opinion, this is one of the reasons why we could not get the ideal zero copy on the data path. So and in my opinion, actually the SK message is not as sophisticated as the SK buff because the SK buff has been involved for decades within the Linux kernel since pretty much the beginning of the networking stack. So SK message on the other hand is, in my opinion, is pretty much is still very naive and very simple. So there are many things compared with the SK buff is still missing there. And if you are already familiar with the Linux kernel, I'm pretty sure you are definitely more familiar with SK buff than the SK message. So in my opinion, this is definitely one of the limitations. Another thing is actually as I briefly mentioned in the beginning is the transparency. So whether we want to hook, regardless of where we want to hook, actually sometimes we do want the transparency to the application because it's usually it's not practical to modify application to adopt their logic to the socket maps, right? So that's why exposing the file descriptor to the user space, in my opinion, is not a good idea, and usually it's a pain point. And managing this kind of socket within the socket map in the user space is not very friendly. And that's why I would argue practically we have to use the socket ops at least for the transparency. So this is actually what we did at ByteDance as well. So we have to use this kind of socket ops. And the socket ops actually there is some limitations there as well. Like I mentioned, so far it only supports TCP socket. Yeah, this is also understandable because there are a lot of TCP state related information which is not applicable to probably to many other sockets. For example, UDP socket, right? So because UDP does not have a three-way handshake. And another thing is actually, in my opinion, it's not very easy to just extend the existing socket ops to other sockets because they are pretty much hard. In my opinion, pretty much hard coded in some way within the kernel. So this could be another limitation for the the flexibility and extensibility. So finally, I would like to show some history and some recent development of the socket maps. So the socket maps actually have been involved for quite some time. Actually, it was introduced in the beginning by John for some socket layer policing, filtering, probably for cinema, I guess. Yeah. However, later actually we realized that actually the socket map could be used for other socket splicing than the TCP socket. So that's why I actually introduced the SKB verdict, for the generic socket maps support for quite some other different socket families. And start from that, actually we added the Unix domain socket and VShock socket support to the socket map as well. Thanks to Bobby here as well. And after that, actually the pretty much the socket map is getting started, evolving quickly and starting to be used widely. Especially, I saw some recent, use case on the VShock here, on the VShock part as well. And recently, actually, my colleague Zijian actually did a very impressive performance improvement for the SK message batching as well, so that actually the performance actually could getting closer to the traditional TCP. And for the looking forward to the future, actually, I do have some ideas, to further improve or further extend the eBPF socket maps. So here are just some of my ideas here, and I'm very open for discussion here. So the first thing on top of my mind is I do imagine we could actually have some generic support for all the socket types for the socket ops, so that actually we could actually do more kind of operation. I mean transparent operation within the socket map combined together with the socket ops regardless of the socket type. So that's my goal. But I know in the reality, this is probably not easy. Actually, I did some very quick estimation here. Looks like the code is not that easy to change. So, however, if people have are smarter than me and have better idea, you are well welcome to do so. I believe this is definitely the right direction to move forward, and I do believe there are definitely real use cases as well. And the second direction I hope we could do is we could have more socket types to support the socket map. So currently we only have literally four types, four types. However, in the future, I do believe we could have more types. For example, even some there are some actually very special socket type like the SMC, the shared memory communication socket. I don't think it even has SKB there. So that's the challenge. So without SKB, supporting the socket map could be very challenging. However, I do offer a very appealing use case here. So with the SMC socket, actually, we could implement the socket map. Actually, we could actually implement the proxying between the RDMA network and the TCP network. So on one side is the SMC socket to the SMC to the RDMA network. On the other hand, is the other SMC socket connecting to the TCP network. They are completely transparently proxied if we could have this. So this is very appealing. So. And the third direction I believe is I'm trying to work on is I hope the data path for the SKB redirection of the within the socket map could be more optimal. Ideally, should be zero copy. However, there are some implementation details within the kernel. The first thing is the SK message. It is a blocker because it is a blocker for our further optimization here. So I hope maybe we could decouple the SK message from the SK buff data path so that they will no longer have to convert from the SK buff to the SK message anymore. And the other thing is, when we redirect to the transmission side, actually the kernel implemented with the send message. So this is another thing we should improve because the send message actually accept some socket message, not the SKB message, not even the SKB, the SK buff, the SK buff. So that's why there is a copy there, which in my opinion is very less efficient. So that's why I believe we need to replace that one with some just replace the SKB from the ingress side to the egress side, but place it directly on the transmission queue. And the last thing is, I do hope maybe we should have some unified way to implement the transmission side and the receive path because otherwise they differ a lot, right? So on one side is the message, on the other side is the socket buff. And if we could actually have some unified way, and I hope maybe we could actually replace the KCM socket, maybe. So that's my opinion. Okay, I think that's all I have today. So I know probably I ran a little bit out of time. So if you have any questions, feel free to let me know.
Hi, thanks a lot for the presentation and thanks for providing all the examples and sample programs in your slides. I think it's like really useful for people who are just like getting started. I had a question about, maybe it's more of a general question, but the filtering example that you showed, where you just, the simple filtering example on a port. I was wondering, did you do any benchmarking? Because I'm really curious, like what the performance would be, filtering with an eBPF program like this versus just like a net filter, like rule or something like that to, drop packets that have a destination port of 8080. I was curious if you've done any performance testing, between different methods to sort of get a sense of how much faster it would be to implement it this way if you were just doing a simple drop like this.
Oh yeah, actually, to be honest, I did not have time to run this program. Actually, when I prepare the slides. However, I think with this example, actually, I think you could actually do some benchmarking. And also, it also depends on how you compare, right? So if we compare this with the traditional, let's say, the traditional way use, let's say, TC filter or the net filter to do this kind of filtering, I think the eBPF way is probably more efficient than the traditional way. Yeah, or maybe you are comparing with doing filtering than without doing filtering. I do believe there definitely should be some overhead, but should be some small overhead. Compare with no filter. Do I answer your question?
Thank you for the presentation. I have a question regarding the zero copy socket buffer redirection that was mentioned as a future direction. What would be so I'm interested about the performance. What would we save, like SKB clone or SKB copy, or because I mean, it's already happening in the kernel, so you don't really have to pass the stuff to the user space. But inside the kernel, what would be what we can save with zero copy? Thank you.
Oh yeah. So here actually, it's as you mentioned, is similar to the. It's not as KB clone, so it's some data copy. So for example, when we use the SK message to send out the data from the ingress to the egress. So actually, on the egress side we have the SK buff. And on the egress side, because we use the send message, actually it needs to be translated. It needs to copy the data from the SK buff to the socket message header for the as a parameter to the send message. So there is a copy there.
Okay, I see. Thank you. Thank you for the answer.
Thank you for the presentation. I just wanted to ask if you can reshare your slides. I saw it on your website, but if you can please share the updated version. Those examples look very interesting. Looking forward to trying them out. Thank you.
Sure. I will upload it to the Netdev website. Thank you.
Thank
If there's no other question, I think that's all I have today. Thank you so much for joining my session.